Greetings and salutations here. Mr. Sutton bringing you the IM3 Honors 4.8 lesson on max and min. Specifically for this one, we are going to be finding minimum and maximum values for real-life quadratic situations. As a quick warm-up for this one, define the following two things, minimum and maximum value of a function, and then say where you would find these on a quadratic function, which is graphed as a parabola like in this graph here. All right, so the minimum value of a function, that is the lowest y value of a function, like this spot right here on the first parabola, and the maximum value of a function, that is the highest y value, like this top of the parabola right here. So the key here is that these are y values, these are output values. And the location is, as you can see in this graph, always going to be at the vertex of the parabola, the turnaround spot. For our first example, we have the height in feet of a rocket after t seconds given by this h of t formula. We want to find the maximum height that the rocket attains. So our strategy on all these max-min problems, since the maximum value always occurs at the vertex, we first need to find the input or x value of the vertex. So let's start by doing that on this problem. So for the vertex, well, we've found vertices before for parabolas. Pause the video and see if you can find the x value of the vertex for this, or in this case it would be the t value of the vertex. All right, since this is almost in standard form, I'm going to start by putting it in standard form by rewriting it with the quadratic term first. So I can write h of t equals negative 16t squared plus 224t. And now that this is in standard form, I can use my vertex formula, negative b over 2a. That's going to equal the t value of the vertex, the input value of the vertex. So that's going to be negative 224 over 2 times the a value, negative 16. And I'm going to use a calculator for pretty much this whole lesson, so I'll just plug this in the calculator now. To make my life a little bit easier on doing this division, I did alpha y equals to pull up fancy fraction mode, and plugging all those in and crunching that, we end up with, exactly 7. 7 what, though? This is a real-life problem, so we need real-life units. So the rocket attains its maximum value after 7 seconds. That's the input units here. 7 seconds. All right, now we're not really interested at the time because the problem is to find the maximum height the rocket attains. So how would I figure out how high the rocket is at 7 seconds? Well, we have a formula right here, h of t, that tells us the height after t seconds. So this is going to be our general strategy too. We're going to plug the x value we just found of the vertex into the original function to find the output value of the vertex, the y value, if you will. So in this case, we're plugging 7 into h of t, so that's 224 times 7 minus 16 times 7 squared. Or you can use this rewritten one where the quadratic term comes first, either way. And then let me plug that in the calculator. So plugging that in off camera and pressing enter yields a value of 784, and that's feet, the units in the problem, so 784 feet is the maximum height this rocket attains. Here's another example for you to try out. In this one, we're preparing a stew with C chefs, and if you tell me how many chefs there are, I can tell you, based on this formula here, this T formula, how many minutes it will take. We want to know how many chefs should be assigned to prepare the stew in the least amount of time, and what is this minimum time? Now, you would think the more chefs you have, the better, right? But at some point, the kitchen becomes overcrowded and it becomes counterproductive. So pause the video and see if you can wrestle with this one. All right, now just like before, we need to find the values of the vertex. We need the number of chefs and the time at the vertex. Since this is an equation in standard form, a quadratic in standard form, we can use negative b over 2a again. This time around, we're looking for the vertex c value. C is the input here, which is kind of weird with time not being the input. So I've got cv equals negative b over 2a. So we've got negative 12 then for that b value over 2 times, this is an invisible 1 next to the c squared. And that's really 12 over 2, which is 6. So this is saying that we should have 6 chefs as the ideal number. Now, how long will it take them if there's only 6 chefs preparing this thing? Well, let's plug 6 back into this t formula to find the vertex t value. So we've got 6 squared minus 12 times 6 plus 72. And I could probably do this without a calculator. So this is 36 minus 72 plus 72. Well, that works out. The 72's cancel, and this is going to be 36 minutes. Bon appetit. For this example, we have a rectangular dog kennel constructed alongside a house, like in the picture up here, with 60 meters of fencing. The house is one side of the kennel. We want to find the dimensions that result in the greatest possible area and also find that area. So we're finding a few things. We're trying to find the length of, for example, this dimension here, this other dimension, and of course the area that results from that. So if we find the dimensions, we can then plug it into some kind of formula to find the area. So our first task on this, I recommend you draw a picture and try to create a function with only one variable. You need some kind of function in any case if you're going to try to maximize this. So I'm going to start with a picture. We've got a rectangular kennel, and we've got a house as one side of this kennel. Now, if we're trying to create a function in terms of one variable, our function that we're trying to maximize, we're trying to find the greatest possible area. So we're trying to build an area function. That means I need to know something about the dimensions of this house, or at least how they're changing. So the more fencing I add to, say, this side of the house, the less fencing I have for this other side of the house. So that's really what I have to change here. Or the more I add down here, the less I have for these here. But we got to start somewhere. So I'm going to make this side here be x. That's what's changing. This is x meters. And I do know that this other side here, since it's the same length, since it's a rectangle, this side must also be x. But how about this other side? How can I describe this side in terms of x? I mean, I guess I could call this other side y, but it'd be nice to have one variable. Because if you only have one variable, you can actually make a function that you could find a maximum value for. So in terms of x, if you've used up x meters here and another x meters here, if you've used up 2x meters of fencing, how much is left for this third side? Well, we started with 60 meters. So that means we must have 60 meters minus the 2x that we've already used. So we can write this third side as 60 minus 2x. All right, let's build a function now based off these dimensions. So the area of a rectangle in general, we know that's going to be length times width. But now let's actually express that in terms of x. Again, we just want one variable. Our length in this case, I guess it doesn't matter which side is which, but I'm going to call it this 60 minus 2x side. And then the width is this other side that has a length of x. And at this point, we're trying to maximize this formula. Well, just like maximizing any parabola, you're trying to find the vertex. So how can we find the vertex of something in this form? Well, we've done intercept form before, finding the vertex to graph parabolas. So with intercept form, you just have to find the zeros and then average them together. So what are the zeros of this function? Well, the value of x that zeroes out this first factor, that's going to be, let's see here, if you subtract 60, divide by -2, that's going to be 30. And then to zero out this other factor, which is just x, you just have to have an x value of 0. So those are our two zeros. We know that the vertex is always exactly halfway between those. It's the average of those. So averaging these together, 30 plus 0 over 2. And by the way, this x of the vertex, this is going to be the width dimension that we're being asked to find in the problem. So I'll just say wv equals xv, just so I lump all this together. So averaging these together then, we've basically got 30 over 2, which is 15. So that's 15 meters that's going to be the width here. Well, now that we found that, we need to find the length. To do that, we just have to plug this 15 that we found for x into this 60 minus 2x formula. So I'm going to say the length of the vertex length, is 60 minus 2 times 15, basically 60 minus 30, which gives us 30 meters. So our dimensions then, we're going to have a 30 meter by 15 meter pen. Now we need to find the area. So there's a lot of ways you could find the area. I mean, you've got this formula up here in terms of x, and you certainly could use that. But we also know that area is just length times width. And we've already found the length and the width. We could just say the area is our length of 30 times our width of 15. And 30 times 15, that's just going to be 450. And that's going to be square meters. Here's another area problem to play around with. You have a 200-foot roll of fencing in a large field we want to construct a rectangular playground area. We're just doing rectangles here. We want the dimensions of the largest such yard and that largest area. So kind of like the last problem, but a little bit different because now we can't use the side of some building as one of our fences, one of our sides. So pause the video and see if you can get a formula in terms of x to describe this situation. And don't go any further because we're going to bring it together to make sure we have the right formula. All right, so I'm going to draw a picture here. Here's my rectangle. And again, I don't have the side of any building as one of the sides here. So again, I have a choice of how long I want to make one of these sides, and that's going to determine the length of the other sides. Let's say I make this side here x. I got to pick something. Well, that means this other side here also has to be x because they're the same length. And what about these other two sides? So there's 200 feet total. We've used up 2x of that. So you might have been thinking, kind of like the last problem, well, maybe this other side down here is 200 minus 2x. But that doesn't tell us how much is left over for just this one side. This is how much is left over for both of these sides. We have to divide this 200 minus 2x of fencing up between these two sides. So to figure out how much each side has individually, we just have to take this and divide it by 2. That means each of these other sides actually has a distance of 100 minus 1x. And this side is going to be the exact same as this side down here. So these are both 100 minus x's. All right, so that is our setup in the picture. So in terms of our formula, we're still doing length times width. So we have a length then of, I guess you could call this 100 minus x as the length, and x is our width. So there's a function in terms of x that describes the area of this pen. Pause the video and see if you can finish this one off. All right, so just like example 3, we're going to find the zeros here and average them together. So we've got 100 for the first 0 and 0 for the other one. 100 plus 0 divided by 2, and again, this is giving us our width, our x of our vertex here. That's going to be 50. So we have a width of 50 feet. Our length, that's going to be 100 minus the x that we just found, 100 minus 50, and that's also 50 feet. So it turns out that the best usage of area is achieved if you have a square, if you're allowed to impact all sides instead of having that one side decided for you, like in example 3. Let's actually find the area then. That's going to be 50 times 50, length times width. So that's just going to be 2,500 square feet. Before we can do our last example, I need to introduce a new form of parabolas. So we have parabola vertex form that we haven't really gone over yet. We've gone over intercept form and standard form. This is a new one. It has the following format. We have f of x, or y you could call it, equals a times x minus h quantity squared plus k. Now you've probably seen things in this form, but you didn't know it was a special form. This is a special form because it turns out the vertex of a parabola in this form is going to be h, comma, k. So if you see something in this form, whatever is being subtracted from x inside here, that is the x value of your vertex. Whatever is being added out here outside the squared parentheses, that's the output value, or the y value of your vertex. So something in this form, very easy to pick the vertex out of. With that in mind, let's use this problem. So the number of times Rick's wife snores, we'll call that S, after T hours of sleep is given by this S function here. We want to know how many hours after falling asleep she achieves her maximum snorage and how many times she snores during that hour. So based off this vertex form and what you know about finding mins and maxes, pause the video and see if you can answer this question. All right, so we know that the maximum snoring is going to happen at the vertex of this formula. So let's write out the vertex first. That's going to be 3, because we have t minus 3, so 3, comma 123. And then the maximum snoring is going to happen at 3 hours, because that's the input value of the vertex. And the amount of snoring that happens is going to be the output at the vertex. That's going to be 123, snores per hour. So there we have it. So hopefully you made it through this one without getting in some snores of your own. Until next time, Mr. Sutton signing off.